Okay, hello everyone. Welcome back. Here we are now going to talk about acids and bases for lecture 8. Historically, chemists have classified substances that behave like acids, such as vinegar as acids, or something like wood ash as bases or alkalis. So basically, things that behave um, that are kind of like the opposite to an acid. So acids and bases, they're kind of think of like opposites to each other. So for example, acids, they have a sour taste and sharp odor. They turn litmus paper red. So example are vinegar, like 4% acetic acid, lemon juice, citric acid. Milk turns sour when it spoils because of the formation of lactic acid. Then butter and like meat products, they have a sharp, unpleasant odor from compounds like butyric acid, from when like fat spoils and it goes bad. So many foodstuffs are they tend to go bad because they do form these acid compounds, and they tend to not have pleasant smells. Okay. So another thing about acids, they can dissolve most metals. Zinc metal will react. It reacts very rapidly with hydrochloric acids to form zinc chloride and hydrogen gas. So we kind of think of them as oxidizing, pretty much oxidizing agents, and then they get in turn reduced. The hydrogen in turn gets reduced. So, so those are some characteristics of acids. Bases, they take their bitter taste, and they turn litmus paper blue, and they're pretty much slippery to the touch, and that's because I think they dissolve oil, so they actually react with oil, and so they tend to remove the oil from your skin, and that's why bases are considered hazardous to us. And acids, they can actually react or give us chemical burns because of the high pH, the high concentration of like acid molecules will produce very reactive ions, and that is not that's not safe to have ions just around our skin and stuff like that. Okay. So bases are also used. Example of a base is a degreaser. It contains potassium hydroxide, a strong base, and that's used to remove grease from ovens. So if you ever have a degreaser, you spray your oven first, let it sit, and then you can wipe off the residue with a wet sponge. And that's because potassium hydroxide converts the grease into a very soluble molecule that's now a soap. So now you can just wash it away with water. Okay? All right. Bases, they become less alkaline or basic when they're combined with acids because they are polar opposites, so they tend to react with each other to form water. So usually when we do a chemical reaction, we say, okay, let's neutralize our acid by adding a weak base, or let's neutralize our strong base by adding a weak acid so we can make sure our mixture is pH neutral or has not an acidic or basic solution. Okay. For example, and we try not to add strong acid, concentrate strong acid, and concentrate strong base because you'll get a very vigorous reaction. So usually when we neutralize something, we won't use strong acid and strong bases together. Usually when we want to try to just neutralize something, we use a weak acid with a strong base or a weak base with a strong acid. Okay, so that's all you need. You don't need to use a very strong acid or base with a strong base or acid. Okay, so the reaction of a strong acid and strong base, that's called neutralization. So let's write the balanced chemical reaction between HCl and sodium hydroxide. So HCl, say we have a solution of HCl. Okay, plus sodium hydroxide. Okay, so let's predict the products. So a neutralization reaction is another name for a double replacement reaction. So essentially, the hydrogen is going to pair up with the hydroxide, and the chlorine is going to switch partners and pair up with the sodium. So we get sodium chloride plus water. So we're getting more water in this case. Our solution is just going to prepare more water, and we'll have sodium chloride dissolved in the water. Okay, so that's what we call a neutralization reaction, and everything is balanced here, so we don't need to do anything else. There we go. So this is something we should absolutely know too, and we'll talk more about chemical reactions when we do the chemical reaction lab. But for our purposes, I do expect students to be able to translate word descriptions into a balanced chemical reaction. So that's definitely something I do expect from everyone. Okay? So HCl, sodium hydroxide, sodium chloride, and H2O. So this is called a neutralization reaction because the pH of a sodium chloride solution is pretty much around 7. So pH is around 7 equals the pH. So we'll talk more about pH today. And then these solutions, pH is around 1. And here the pH is around 12. So very different pHs. So when we do react an acid and a base, you'll get a very a pH value that's kind of right there in the middle. And if we did that, it's pretty much around 7. Okay? All right, so now let's talk about what makes an acid and a base. Let's get down to the kind of chemical terms here. So we have a very, the first kind of definition for an acid and base was based on Savant Arrhenius' example. So Arrhenius did a lot of contributions to the our fundamental understandings of many concepts in chemistry, and one thing he studied was acids. So acids and bases. So it was a pretty important contribution here to determining what's an acid and what's a base. So our Arrhenius acid is a compound that dissociate or ionizes when they dissolve in water to give hydrogen ions, so H plus ions, and a corresponding negative ion. So for example, we have HCl, and if we look at this picture here, we see that the ions are completely dissociated and surrounded by water molecules, and see our Cl-, large Cl- ions are surrounded by water molecules, and our H plus ions are also separated, and see they're no longer molecules in solution, they're ions. So they're completely separated. The HCl molecule is now fully dissolved but separated as ions. So now that is what an acid typically is. When you dissolve it, the concentration of H plus increases. So this is the example between HCl. So you can take HCl gas, you put it, you seal it over a solution of water, and eventually you'll get HCl. You'll get a HCl solution, a very acidic solution, containing H plus and Cl minus ions in water. All right. So for this example, let's write out some the ions when the following dissolves in water. So these are all examples of Arrhenius acids because, for example, perchloric acid will give us H plus ClO4 minus. So it won't dissolve into chlorine and oxygen. It'll just stay as the perchlorate ion. Okay. So every time we have dissolved in water, we will get a series of these ions being produced in water. HBr, same thing, very strong acid. We get H plus Br minus. So you see here, our definition does match with all these compounds. You're producing H plus and a negative ion. HCN, a very toxic gas, but like HCl, it can dissolve in solution, so you get H plus. Plus Cn minus, so that's cyanide ion. And then lastly, we have H2SO4, that is sulfuric acid, another strong acid, and it will give us H plus H bisulfate ion, HSO4 minus. Okay, so that's an example of Arrhenius acid. When it dissolves in water, the molecule dissociates into hydrogen ion and a negative ion, like in all these examples here. Okay. So, in summary, Arrhenius acid, I pretty much just went over the summary. It dissolves in water and produces the hydrogen ion H+. All right. Now let's go to an Arrhenius base. So compounds that dissociate in water to give ions. So it should say hydroxide ions. So let me just fix that right here. So that should say hydroxide ions. Hydroxide ion and a positive ion. Sorry about that. I guess that I kind of messed up there. So, for example, sodium hydroxide dissolves in water to form a positive ion from the metal, sodium, and hydroxide ion. So it's not O2 minus or O2 minus and H plus, it's OH minus. So the hydrogen atom, the OH bond in hydroxide does not dissociate because that's too energy unfavorable. So it exists as OH minus. So let's write some examples here. Rubidium hydroxide. The metal will ionize to Rb plus OH minus aqueous. We have potassium hydroxide, much like, so these are pretty much all similar to sodium hydroxide in that they have a metal and then a hydroxide ion. The only the calcium is so rubidium, potassium, and lithium are all in the same group as sodium, the alkali metals, so they form very strong basic solutions. But the alkaline earth are also pretty strong bases as well, but they tend to be less water soluble. So we have H2O here, K plus OH minus. So we do see a trend here. Then calcium. So in this case, we're going to get calcium 2 plus 2 OH minuses because there's now 2 hydroxide ions per calcium ion in our formula. And then lastly, lithium reacts with water. Sorry, it doesn't react with water, but dissolves in it to give you lithium plus OH minus. Okay? There you go. So in summary, a base is any substance that dissociates to ions when it's dissolved in water to give hydroxide ion and OH minus. Okay. So now let's classify the following compounds as either an Arrhenius acid or base. Okay. So the first one is nitric acid. So nitric acid dissolves in water to form H plus and a negative ion. So this is an Arrhenius acid. magnesium hydroxide will dissociate to magnesium ion and hydroxide ion. So this is going to be an Arrhenius base. And then lastly, acetic acid will dissolve in water to form hydrogen ion and acetate ion, a negative ion. So this is also Arrhenius acid. There we go. Okay. All right. So that's a pretty a brief consideration of what makes an acid and a base a base. But you see, these definitions, they kind of fall short because we know that a molecule, any compound can act as an acid or base, given that it becomes that it loses hydrogen or gains a hydrogen atom. That can gain a hydrogen atom, hydrogen ion, or lose a hydrogen atom to become a negative charge. That can also qualify as an acid or base. So we're going to talk about now the other definition of an acid or a base, and that's the more common one we see nowadays in terms of what makes an acid and a base is the Bronson Lowry definition of acid bases. So this one is a good, very more robust definition, and it can describe compounds that don't produce H plus or OH minus in solution as acids or bases. All right, so following the Arrhenius example, Johannes Bronson and Thomas Lowry, they independently proposed a more powerful set of definitions to classify more compounds. So we can classify other compounds as acids or bases. Okay, so we look at the model here. We see here that the Bronson model, we assume that the HCl molecules will donate an H plus ion to water molecules to form what we call H3O plus. That's the hydronium ion. So it's basically protonated water. And then Cl minus, it also still produce Cl minus when HCl is dissolved in water. So what are the key definitions here? Well, an acid is a proton donor. It donates protons, so it donates H plus ions to another ion or molecule, which acts as the base. Okay? So in this model, HCl doesn't dissociate into H plus and Cl minus because these ions are really reactive. So we assume that the H plus is being associated with a water molecule. So we call it hydronium. So that's probably the best kind of picture to think about a water and a proton interacting. It's not just H plus in solution. It's probably a mixture of H3O plus and then that proton being shuttled between different water molecules. Okay. So instead we say, okay, HCl plus water gives us H3O plus Cl minus. So from here on out, I'll interchangeably use H3O plus and H plus, but the more accurate picture is H3O plus, but they essentially mean the same thing. Okay. So here is what it's more appropriate to think about how a proton interacts with water molecules in the picture below. You see here that the hydrogen ion, the hydrogens, the water molecules are going to arrange themselves and kind of interact with the protonated water molecule through what we call hydrogen bonding. And we'll talk more about that much later in the course as part of our last topic. But you can see here that water gets protonated, then it can interact, the hydrogen can interact with other water molecules, and so we kind of associate protonated water as H3O plus. All right, so we think of it as solvated H plus ion. Okay. All right, so let's just go over these terms here, and then we'll come back. We'll pick it back up in the next video. So we can represent the same reaction now with some terms from our model, Bronson Lowry model. So HCl, that will be the source of the H plus ion. So we say that's an H plus ion donor. And if we look to the right of the molecule, we see here that the water molecule is accepting a proton, right? So, or H plus ion. So a proton and H plus ion are the same thing, because once you lose an electron from a hydrogen atom, all you have left is a proton in the nucleus. So we tend to call the hydrogen ion a proton too. Just a proton. So H plus donor, and we see here the water is picking up that hydrogen ion, so that's called the H plus ion acceptor. And if we compare the HCl and Cl minus on the right, we see it's lost its proton, so we say HCl is the proton or H plus ion donor. Okay, and to summarize here, we say a Bronson Lowry acid is any substance that can donate an H plus ion to a base, which picks up that proton. And then a Bronson Lowry base is any substance that can accept an H plus ion from the acid. So these two things must occur for an acid-base reaction to happen. Okay? All right, so we'll stop there and pick up in the next video. So see you then.